Hi there. So in the previous video, I demonstrated how to simulate the potentiometer with load and without load. In today's video, I'll be demonstrating on how to simulate the Wheatstone bridge using the potentiometer, Rx over here, and three different resistor values, R1, R2, and R3. Alright, so the middle point here is the voltmeter. It will be a measuring point between the points VA and VB, and then we have our VS as our power supply. Okay. So components that we are going to be using for the simulation. So a 10 kilo ohm potentiometer, alright. And then for the unbalanced bridge, we have three resistors, 1K, 2K, 3K. And then for the for the balanced bridge, then we have six resistors ranging from 1K to all the way to 6K, alright. And then, yeah, as I said, 5 volts as our power supply, a ground, and multimeters to measure across R1, R2, R3, Rx, and also the point VAB, right? So now, the Wheatstone bridge, there is actually two types, which is one is the unbalanced bridge, and one is the balanced bridge. So what's the difference is that for the unbalanced bridge, we will keep our values of resistors R1, R2, and R3 constant, right? The one that changes the value is the potentiometer over here, right? So therefore, you can see that the reason why the equation says VA is not equal to VB is because since these three values are constant, therefore the points VA to VB to meet, right, to be equal to each other will not occur. Only at one point it will be equal, but just because we are changing the the potentiometer values all the way from maybe 0k to 10k depending on what you're looking for. So in this simulation, I'm just doing three different values of the potentiometer scenarios, right? So let me just scroll it down a little bit. So you can see here I've actually done the calculation side of the unbalanced Wheatstone bridge. So you can see that our R1 is going to be 1k, R2 2k, R3 3k. Right, our Rx here for this image here right now, right, I'm putting it as 5k, but throughout the scenarios this Rx value will change. Okay, so let me show you what values that we actually going to be using it, right, the Rx value. So we'll be using it as 1k, 5k, and 10k. So I've done the calculations here, so later on I'll slow it down and then you can just glimpse through. It's a pretty straightforward VDR calculation, right? So as you can see, the Rx right now is 5k, right? And we've already know that since this is an unbalanced Wheatstone bridge, so the V out is not equivalent to 0. Therefore, we are concluding that R1 over Rx is not equivalent to R2 over R3, and to say that VA is not equivalent to VB, right? That is our statement over here. VA is not equivalent to VB. So as you can see, right, we are going to be doing the scenario 1, where scenario 1, as you can see, our three scenarios here actually, R1 to R3 is constant. The one that changes is Rx. So now scenario 1, our Rx is 1k, right? R1 1k, R2 2k, R3 3k. So let's go into the calculation a little bit before we simulate, right? So since we want to find the voltage at V1, right? So we're going to take the R1 value, right, divided by R1 plus Rx. So we're going to be setting our potentiometer resistance value at 1k, right, for the first scenario. So our Rx is going to be 1k. So 1k divided by 1k plus 1k, right, multiplied by the voltage supply. So we will get 2.5, right? So since the resistance value R1 and Rx are equivalent, right? And since this is like a series connection where it is parallel to the voltage, so the voltage will split equivalently, right? Because if here is 1k and here is 1k, so the voltage over point here will be 2.5 volts and 2.5 volts, right? So V1 2.5 volts, Vx 2.5 volts. Now for V2 and V3, so over here, right? So as you can see, the resistance value are not the same, right? For R2 is 2K and R3 is 3K, and they are again parallel to the voltage source 5 volts, right? So after we done the calculation, where we get the formula is R2 divided by R2 plus R3 multiplied by voltage supply. So you get 2 divided by 5K multiplied by 5 equals to 2 volts, right? So same goes for V3. You do the calculations, right? Formula and calculations, you get 3 volts. So we know that VAB equals to VA minus VB, right? And if you are saying that VAB is actually VA minus VB, so it means to say that this point is Vx, right, minus V3. So therefore, we take VAB is equivalent to 2.5 volts minus 3 volts. So we get negative 0.5 volts. So in scenario 1, the voltage across over here from point A to B is actually negative 0.5 volts, right? So that is for the first scenario. Okay, so for the second scenario onwards, you can check it out, right? I'm not going to actually go through each scenarios. I've provided you with the calculations, but you need to do your own homework as well, right? So yeah, so scenario 2 is for 5 kilo ohms, right? So similar calculations, just substitute the Rx with 5K and you will get your values, right? So the VAB here is 1.167, and for scenario 3 is 10 kilo ohms. So we get the VAB again to be 1.545 volts, right? So do the substitution of just changing the Rx values and you will get your V1 and Vx values. Okay, so as you can see that the calculated, so calculated is actually being calculated over here for you, as you can see. Now for simulated, so let's go into the simulation side now, right? So usually before you do the practical or simulated side of the experiment, you need to do the calculated, and this is because you can easily verify your simulation answer and your calculated answer, right? So over here we have already done our calculated side. Now we're going to be checking with our simulated side. So let's go into the simulation, right? So we're going to use this as our base image to draw our circuit, right? So now launch your Multisim, right? So remember, right, the shortcut buttons to perform the simulation. So in order for you to find the components, so let's just use Control W, right? And then yeah, make sure you go to basics and then go to potentiometer, and we take in the 10 kilo, right? And then flip it, alternate Y. Now we need 3 resistors, so Control W again, and then is the resistors? Yeah, 1K, and we're gonna be just copy pasting it. So okay, I think we should have gone with, yeah, it's okay, we will just leave it as it is. You can change it, it's not an issue. So label, we just label it as RX, right? Label this as R1. Okay, and Control R to rotate it. Now we're gonna copy it and paste it, copy it again and paste it. We're gonna be changing this value to 2K, and also this one to 3K, right? Now we need a voltage supply. So sources, right? Power sources, DC, right? Put it here, and then we need a ground as well, right? And there we go. So now let's do the connections. Okay, sometimes yeah, it takes some time. Don't worry, it's the same thing. Now, so this one here, should we leave it floating? No, right? We should actually connect it. Okay. Sorry about this. Yeah. This is not supposed to be here. It's supposed to be here, right? But let me push it down a little bit. Okay. Yeah. Now over here, usually we'll ground it, right? So we just take this ground, copy it, and paste it. That's all. And we're good. Okay. Now we need to change this to 5 volts, right? Now, in order for us to identify what we're doing is right, so what we need to do, we need to put a voltmeter, right? So over here, we're gonna be putting a voltmeter. So drop that here, right? So in order for me to show all the, how to say, how do we obtain the calculated side, whether it's how to say, like equal between the calculator and the simulated. So we're going to put actually another 4 more multimeters to measure, right, the voltage across each of the resistors, right? So rotate. Okay, I think let me, yeah, it's already voltage. So this will be for this. All right. So now this is our VAB, okay, and then let's take our this one here and here, XM2 to be here, and XM3 to be here. So we already know that we are taking Vx minus V3, right? So this is actually XMM4 minus XMM3, right? This minus this, and you will get the VAB value here, right? So now just double check everything, connection is fine. So let's, okay, yeah, before I forget, we are actually taking our Rx to be 1K, right? So we need it to be at 10%, okay? Yeah, so 10% is 1K, right? If you're not sure, maybe you can just redo the previous lab, right? The potentiometer lab, so that you can identify regarding how to use the potentiometer again, right? Now, so there we go. So as you can see, right? Negative 2.5 volts, 3 volts, 2 volts, negative 2.5 volts. Okay, so the reason of how to say I'm getting negative here, right? It's very straightforward. The reason why you're getting negative is because the direction of the probe, right, for the multimeter is wrong. So what you need to do is you need to flip it. Sorry, alternate Y. Yeah, not control Y, yeah, alternate Y. So now let me just put it there. Okay, so same goes over here. So I need to delete this and this. Yeah, alternate Y. So now we're good. So let's see, and voila. Oh, sorry. Yeah, so you see, positive, 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 positive. You're getting negative is because we're taking 2.5 volts as the point Vx minus the point at V3, right? So it's 3 volts. So 2.5 minus 3, you get negative 499.998 millivolt, right? So it is actually 500 millivolt, right? So as you can see, negative 500 millivolt, right? So continue to simulate for 5 kilo ohm, all right, and 10 kilo ohm. So let's see. So I think it's quite, yeah. So you can just change it to 5k. So 5k means 50%. So 50%. So you see, 1.167. So yes, it's correct, right? And the next one is 1.545 for 10k. So for 10k, so it means at 100%. And there we go. So this is part one of the unbalanced bridge, right? So for the balanced bridge, okay, so let me stop this. Now for the balanced bridge, right, it is basically we are taking the points VA and VB to be equivalent, right? So when we are taking the point to be equivalent, so it is saying that VAB will definitely and always be equivalent to 0, right? So it is to say that R1 over Rx is equivalent to R2 over R3. Therefore, each time that we want to, how to say, when we are changing the R1, R2, R3 values, right, the resistor values, we can calculate the Rx value to be set at in order for us to obtain a VAB equals to 0 value, right? And therefore, it will be saying that VA is equal to VB. So in this balance bridge, all right, I've done 2 scenarios, but you can try more, all right? I'm just going to be demonstrating on actually how to simulate it for these 2 scenarios right now. So I've set my R1 to be 1K, R2 to be 6K, and R3 to be 3K. So using the formula over here, right, I calculated the Rx value. So when I substituted, I get 1K multiplied by 3K divided by 6K. So I get 0.5K, right? So Rx needs to be set at 0.5K in order for the VAB measured to be 0, right? So as you can see, calculated. For the scenario 2, same thing as well. I changed the R1, R2, R3 values to be 5K, 4K, and 2K, right? So once I calculated, I get my Rx to be 2.5 kilo ohm, right? So now in the simulated side, okay, let's go to the simulated side. So right now, so let's push this back to 0%, right? I need to change my R1, R2, and R3 values, right? So my R1 is still 1K, R2 6, and R3 3. So the only value changes here is this. So double click on it, change it to 6K, right? Now, I'm not going to directly increase the percentage right now. I'm just going to use the keyboard button A to, how to say, increment by 5%, right? To show you that I'll get 0 actually eventually. So right now, right, it's negative. Okay, so at 10K, I need to be at how many ohms? 0.5. So I just, sorry. So there you go. I just press once the key A button, right, on the keyboard, and I get 5% increment. 5% means 0.5 kilo ohm, right, of 10K. So I increase. So you can see that point A VA here is equivalent to point VB, right? Because we are measuring VAB. XMM1 is measuring VAB, which is, you're supposed to get 0, but this is actually, yeah, it's supposed to be 0 actually, but it's showing microvolts. So we are assuming it as 0, okay? Because you see, we already know that Vx, right, the voltage across Vx here, the potentiometer, is 1.667 volts, and V3 is also 1.667 volts. So you take this and minus this, you should get 0. Okay. When it's microvolts, there is actually no voltage at all in that circuit. Alright. So now let's stop this and do the second scenario. 5K, 4K, 2K. Right. So change this to 5K. And this is 4K. And this is gonna be 2K. So now our Rx value is to be 2.5. So let's run it, and I'll just press my keyboard button again. So now it's at 5%. So 2.5K means it should be at 25%. So 10%, 15%, 20%, and 25%. So there we go again, right? So it's the same thing. So you see, previously it was at microvolts, now it's at nanovolts. So it's nano means 10 to the power of -9. Micro was 10 to the power of -6, which is super small, right? So we can neglect when it's at nano or micro, right? Even for millivolts, we'll convert it to volt to identify whether it is, the voltage is there or not, right? So if it's like 0.5 millivolts, yeah, there is not much voltage there actually. When it's 500 millivolts, meaning that it's 0.5 volts, right? As how we had in the first scenario here for the unbalanced bridge. Okay, so that is all for this video. Thank you.